Wow, what started that off? What did I just say that made everybody just start talking? That was really weird.
Oh, then I was just talking about water.
Okay, I thought that was bizarre. PlayPosit due dates, both in Canvas and in PlayPosit, are suggestions, so don't panic about those. Okay. Ideally, I've picked the due dates for those to be centered around when we're discussing that content. I've also tried to put the due date for the PlayPosit videos because they're longer and can take more time, in a place where you'd have the weekend to review them. Okay, so the due date for those is usually on a Monday, assuming that you have the weekend to go through and watch it. Okay. Canvas, meanwhile, has the due date in it, again, so that you realize that you're supposed to be doing that, and that's about it. Unfortunately, the instant I put in a due date into Canvas, Canvas goes, oh, this must be an assignment. Students have to submit something. And if you don't submit anything to Canvas, it will then complain at you that you haven't submitted anything. It will continue to complain at you that you haven't submitted anything until I submit a grade in the proper way that Canvas wants the grade submitted, which half the time I do correctly. Okay? Because Canvas and PlayPosit do not talk to each other, I have to download grades from PlayPosit, interpret them, and then input them into Canvas. That takes a bunch of extra time and effort that I don't think is all that important. So I input grades or will attempt to input grades from PlayPosit into Canvas about every 2 weeks. Okay? So I apologize for Canvas complaining at you, but there's nothing I can do about that. Unless somebody knows how to tell me to not have it complain, in which case, talk to me after class. After that, smart work. I posted an announcement and then edited that announcement and then replied to my announcement to feel cool that people were responding to me on smart work. Okay, there was a question about printing assignments. I went through and built the video just showing that I could do it, so there was video evidence. I did get an email response relatively quickly after that they still weren't able to print. Okay? So I went through and printed out all of Unit 1. Printed out. Okay? It's all in PDF. Okay? I posted all of those PDFs to Canvas. So if you want the printout of the homework, you don't have to go through the download process within SmartWork. The printouts are available on Canvas. I don't think I can get copyright in trouble for that, I hope. Probably shouldn't have recorded that. Okay? So those are available files, SmartWork printouts, Unit 1. I'll try and do that for all of the units, but it'll take time. Shoot, what was this one about? Oh, if you're having problems with finding stuff within the files or finding videos or finding lectures or PlayPosits, I am attempting to update, and of course I'm probably now signed out. Feel free to do that, computer. Thank you. The modules. Right? Within the modules, I have Unit 1 supplemental stuff. Okay? On the outside, the supplemental things are the PowerPoints. So there's 4 PowerPoints that are supplemental for Unit 1. Indented, we have the PlayPosit for that and the YouTube. Because to use PlayPosit, I have to post it to YouTube anyway. Okay? So if you want access to the YouTube video after the fact, you're like, I need to watch that again, or I want to watch it again without the questions popping up, or I want to watch that again at double speed so that that hour that Mike spent is now a half hour, cool, do that, YouTube will do that. So all that should be linked and set up and ready to run right there. Okay? You'll notice with this last one, there's no PlayPosit. I think I've overwhelmed, in my opinion, the amount of online videos at this point for the first unit. So I think I'm going to stop requiring PlayPosit for the first unit. But there's still some online content if you would like to use it to review. Okay, that's looking at manipulating models and the 2-dimensional drawings. Okay. The next part, we have nomenclature. This is throughout the semester. Right? I personally hate nomenclature. Right? It is literally, do you know a rule that somebody invented? If you know the rule, follow the rule. If you don't know the rule, well then screw you, you're wrong. That's nomenclature. right? So I hate lecturing on it. We'll go through some practice every so often, but it is literally just what is the rule. So I tried to break down nomenclature into a couple different sections. They're in YouTube videos. These are now shorter. I think the longest one is 20 minutes. But some of them are in the 10-minute range. Okay, so it's just trying to burn some of that nomenclature. What are the rule kind of content? Okay. We will periodically do nomenclature practice in class, but it's not going to be so much talking about, well, then do this, then do this, then do this. Make sense? Right. If you remember general chemistry nomenclature, pretty much all those rules are invalid. Right? Not necessarily invalid, they just don't apply. Right? But if you think back to the struggles that you had with Gen Chem nomenclature, you probably hated it at first, and then were like, just give me a test on nomenclature every single time, because I'll ace it. Right? Because you get used to the rules. Once you know the rules, you're fine. Same thing happens with OChem, unless you're me. After that, in the modules, we'll have all the lecture videos. Okay, so far, the only lecture I've got recorded was this past Monday. Okay? So you can click that, and it should take you out to YouTube where the video is. Make sense? Questions about that? Let's go back to this. So last thing, if you have questions, ask them. I've already been answering a bunch of questions. I'm happy with answering more questions. It's not a burden. Okay? If you have comments, feel free to tell me. Okay? I'm not calling people out, but I do always hear people talking about particularly past instructors. If there was something that you didn't like that a past instructor did, you should let me know so that I don't do the same thing to piss you off. Okay? I may still do it, but at least you've given me the opportunity to not irritate you. Does that make sense? Okay. I don't judge you, I just go home and cry to myself. Okay? But you don't have to worry about that because that's to myself and not to you, so you don't need to worry. Okay? So let me know if you have questions or comments, and I'll try and adjust and get those things figured out as quickly as I can. At least mediate the damage on your end. Make sense? Okay. Lewis structure. These are the rules that I would specify for, sorry as I'm trying to track down my stuff, that I would give to anybody in general chemistry. So 130, 151. Okay. These are the same rules that hold sort of true for OChem. Okay. The issue with OChem is that we very quickly change and adapt from these rules. In Gen Chem, we have central atoms. In OChem, there's very rarely a central atom. Okay, so we have to learn those rules from Gen Chem and now switch and start applying them more appropriately in OChem very quickly. But if you don't apply these rules from Gen Chem, everything you do in OChem is wrong. And it becomes very difficult for you to actually draw and interpret structures correctly because you don't have the fundamentals for how structures were built. Okay? Those of you that think you're rock stars with Lewis structure, read the rules and you're probably like, I didn't have to do it that way before. That's because the way you did it before was from a general chemistry instructor that didn't like OChem. So didn't understand that they were screwing me over by telling you the wrong thing. Okay? You should be following these rules. You'll get the exact same answer as anything out of Gen Chem. But this sets you up with some reasoning abilities that you can pull and use in OChem, as opposed to Gen Chem that just gets you an answer that you don't have to manipulate. Okay? So, follow those rules. One of the big kind of changes that can come out of this, particularly in theory from 130 to 151, is you're required to assign formal charges per atom. That is a requirement in OChem. If you haven't done that in Gen Chem, you have to now. We need to know where the electrons are on any given atom in any given molecule. Okay, so you have to know your formal charges. Okay? There's a couple ways to go through and do this. The longest way is to go through and calculate it. That's your valence electrons minus the non-bonding electrons minus the number of bonds. That gives you the formal charge for a single atom. So if we move to a structure like sulfate, and this is usually why students groan, sulfate has how many atoms? There's 5. Okay? With 5 atoms, that means 5 calculations. Right? And you would have to calculate formal charge for every single one of those. Okay, so let's go ahead and just pick one. Sulfur, valence electrons, 6 minus the number of non-bonding electrons, 0 minus the number of bonds, 4. The answer is, okay, you'll hear a lot of people go through and say 2. 2's not wrong, plus 2 is better. Specify the magnitude of that charge, be it positive or negative. Okay? That would then need to get written next to the sulfur as plus 2. Okay? Just because I happen to flash on it, sometimes you'll see people write it as 2 plus as opposed to plus 2. It doesn't matter which one you use. Plus 2 makes more sense to me than 2 plus. So I always do the symbol first, then the number. Okay? Let's do one more quick test. Oxygen, because all the oxygens will be the same. There are 6 valence minus how many bonds? 1. Not 4, because it's not how many are in the structure, it's how many to that atom. That bottom atom only has 1 bond. Sorry, I screwed up the order. Minus the number of non-bonding electrons. How many electrons are not bonding on that oxygen? 6. The answer is -1. I would then specify that next to it. The 1 oftentimes gets implied. In fact, every time I do it, I imply it. Right? Typically, we're only dealing with plus 1s and minus 1s, so you'll only see the symbol without the number, and it will be circled. If it's a larger number, I have a harder time circling it, but in theory, I always try and circle the charges to make sure they stand out. Make sense? Okay. By applying formal charge, we could then go through and say why that structure for sulfate was not good, because we have a bunch of charges within it. Okay? And we could go through and show resonance by moving electrons to neutralize those charges and get all of the variety of different structures for sulfate, okay, the resonance contributors. Okay? One of those resonance contributors is shown on the right. If we go through and apply the same logic for our formal charges through, we'll find the sulfur now has a 0 formal charge, because there's 6 minus now 6 bonds, minus 0 non-bonding, gets us a 0. And we'll find that the outermost oxygens, or sorry, the left and right ones in this case, are negative, where the top and the bottom are 0. Okay? That's how we would calculate formal charge. That is the most common way to associate the balance of electrons in a molecule on atoms in organic chemistry. As you may or may not remember from your Gen Chem, not only do we have formal charge, we also have oxidation state, or oxidation numbers. Okay? Organic chemistry tends to focus on the formal charge because the formal charge allows us to predict something about the reactivity. The oxidation state, however, does not. Okay? The reason being is that an oxidation state will stay constant regardless of the number of bonds. The formal charge changes. Notice the formal charge from sulfur went from a +2 to a 0 as we transition between these two structures. Identical molecule, just a slightly different arrangement of where the electrons are, and all of a sudden the reactivity appears to change. The first one is now more reactive because it has more charge. The second one is less reactive because it has less charge. Okay? If we applied oxidation state, what happens? Well, let's take a look at the sulfur in the first structure. And I always do this one horribly wrong, but let's see what I can do. Because it's not valence electrons. It's total electrons. It's accessible electrons, might be a better way to say it. So if we look at the sulfur in this first structure, how many accessible electrons does it have? Does it have access to these electrons? Okay, let's try it this way. Does it have access to the electrons shown in the lower right-hand corner? No. Why not? Too far away. Does it have access to the electrons on the oxygen? No. Why? Because they're on the oxygen. Okay. So the only ones that the sulfur has access to are those 8 electrons. And that's got to be valence. It's got to be valence in this calculation. Sorry. We'll do 6 because it's valence. Minus now the electrons that that sulfur owns. Okay, so there's 8 electrons around it. Does it own any of those 8? Okay. Well, what does it mean to own? Own has to do with electronegativity. Okay. So if we look at that topmost bond, okay, that line, where do those electrons spend their time?
Closer to oxygen.
Why with the oxygen?
It's higher electron.
Oxygen is more electronegative than sulfur, which means all of those electrons are on
Oxygen.
the oxygen. Does the sulfur own any of those electrons?
No.
No. Okay. So it comes out as a +6. If we move over to the other structure, sulfur has how many valence? 6. Does it own any of the now 2, 4, 6, 8, 10, 12 electrons around it? No. Why not?
Oxygen's
Well, oxygen's more electronegative. What happens? You get the exact same oxidation state. Okay? Is that how you calculated oxidation states in Gen Chem? No. What did you do in Gen Chem? Right, we said SO4 minus 2, so the oxidation state of the sulfur plus 4 times the oxidation state of oxygen being a minus 2 has to equal minus 2, X has to equal +6. Holy crap, it's the exact same answer. Yes, that's awesome. Why is OChem different than the Gen Chem method? What happens if instead of this just being a lone pair out here on this oxygen, in fact, let's just change that from being oxygen to now this structure. God, that was horribly drawn. Let's try that again. There we go. Well, now the formula isn't SO4 minus 2. The formula has changed drastically. Can anybody do that math real quickly for me? What was it? C7H. Thanks for doing the math. 7 SO3 minus. Use Gen Chem to solve the oxidation state for the sulfur. You're going to have a really bad time figuring that out. Okay? Gen Chem doesn't allow you to do it from a more complex formula. Add into that, the oxidation state for the carbon that's a CH3 is different than the oxidation for the carbons within the ring. Okay? So Gen Chem assumes every atom in your formula has the same oxidation state, and that isn't always true the more complex your structure gets. That's why we modify to the oxidation state calculation that we show here, and it comes from the structure. How often do you encounter it? Rarely. Okay, but it does show up. You now know theoretically how to do it, or at least where to find it. Okay? Formal charge is our driver. We had, sorry, you wanted a picture of that? You probably wanted a picture of it with all the stuff drawn?
Yeah, the one you...
Yeah, the part that I erased, yeah, sorry. It's recorded. For record, if you want to write it down, it's about 19 minutes. So, if we go through and looked at these, remember we evaluated these two structures, so well, which one is better, which one is worse? Okay? We now have a priority of deciding which structure we should be looking at. Okay? And when we're looking at Lewis structure, our first rule is that our octets must be satisfied. Okay? Everything has to have its octet unless we can't satisfy the octet. And we can't satisfy the octet if for some reason, sorry, the total valence doesn't add up high enough to put enough electrons in to satisfy the octet. Okay? That's the one case where we can't. But for the most part, we should be able to satisfy octets. Okay? Again, the last thing that we can throw in there is if we can't, and hydrogen. What is hydrogen's octet? It's 2 electrons. Right? Every other element will have an octet of 8 electrons. So when we're drawing our Lewis structures, we need to make sure we've satisfied the octet. That makes our structure better than another. After that, okay, because if we look here, both of these have satisfied octets. The one on the right is a little bit problematic because it appears to have exceeded the octet, but it's achieved the minimum. I will minimize charge. So if I go through and account for formal charge between these two structures, remember the one on the right has less formal charge associated within it. The one on the right becomes the better structure. Kind of make sense? Yes? The only reason you can exceed the octet is to neutralize charge. Okay? That really, and now I'm going to hem and haw here, but I think I'm right. That only happens when you're dealing with elements great or in the 3rd row or lower. Anything in the 2nd row will never be able to exceed the octet, and you'll never encounter a case where you could exceed the octet. Okay? If drawing the structure correctly. Okay? So 2nd row and above, which really is just 2nd row, okay? Octet only. Everything has to have at least the octet. 3rd row and lower can exceed if it minimizes the charge. Okay? So let's move to the next example there, because it's a little bit more challenging. Our CH3CO+. If we went through and attempted to use the rules that were just like 3 slides ago, we're going to have problems. We'd be able to total the valence electrons. That shouldn't be an issue. But when we ask to draw a center atom, well, what's the center atom? Right? The least electronegative. Okay, that can bridge, so hydrogen won't be. So it'll be carbon. Which carbon? Okay. Is that a center? What defines it as the center atom? Okay. There isn't a clean definition. This one's still at least a small structure, but if we scale up to larger and larger structures, remember we had that, let's backtrack here a little bit. When I said what happens if we did something like this? What's the center atom there? There isn't one. Okay? So what you're trying to do, or what in theory you were doing in Gen Chem with the simple structures, is picking up the patterns behind how these atoms bond, so that when you move into OChem, you know what their general rules are, so that you don't have to keep using or going back to those rules. And you can start applying a more advanced thought through it. Okay? We'll talk about some of those more advanced rules. In fact, there's a nice summary slide for it, but it's not the next one, so we won't skip ahead. Carbon should have 4 bonds. Okay? So if I look at this, it is written in a way that it's a little bit easier to interpret. I start with carbon. Okay. What is that carbon bound to?
3 hydrogens.
Why are you saying 3 hydrogens and not oxygen?
So you're reading left to right.
Because we read left to right, and the oxygen doesn't show up next to that carbon. Okay, so I would place the 3 hydrogens around it. What should the next thing be? Because there's that 4th bond. Carbon. Why carbon and not oxygen? It's the next in that sequence, left to right. And then I need to attach my oxygen. Okay. Now we're going to potentially run into issues. What would those issues be?
Carbon's not fulfilled the outside.
We're missing 2 bonds for carbon. We're also missing a bond for oxygen if we knew the bonding patterns, and then it still wouldn't have its octet. Okay, so this is where the old rules can come in and help us out. Carbon comes in with how many valence? I see you, I'll get you in a second. 4, there's 2 of them. Hydrogen comes in with 1 times 3, oxygen. 6, the charge means subtract 1 electron. Okay, 8 and 9 is 17, minus 1 is 16. Okay. Everywhere I have lines in black are electrons, right? So I have 2, 4, 6, 8, 10 electrons. I haven't achieved my 16, which means I need to get the rest of those electrons drawn into my structure. There's 2 sites I could place those electrons. Where do I start placing those electrons? Ooh, 2 answers. It's going to be oxygen. Because based on the rules that I told you on that previous slide, where do you start placing electrons? The most electronegative. Oxygen, being the most electronegative, is going to want as many electrons around it as possible, up to its octet. So I will place those missing electrons around the oxygen as pairs. I now have 6 electrons, or 6 lone non-bonding electrons around the oxygen. I now have 16 electrons drawn in my structure, and I have a valid answer. Why are you saying no?
Because carbon doesn't have its 4 bonds, and oxygen
Okay.
moles are double bonded with 2 lone pairs.
Okay, we'll come back. I think we'll come back to the oxygen. Okay, the carbon didn't have 4 bonds. Why do we need 4 bonds? Octet rule. Okay, so another thing I want to address because of the pause in your statement. So I appreciate the adventuresome one going out. One acceptable answer to me asking you what's wrong with it is you being like, it doesn't look good. That's perfectly all right. Okay, just because you don't know the terminology yet doesn't mean you don't have an instinct about that looking like crap. That's okay. Okay, so that is a valid start to that. You added to it, said the carbon doesn't have its 4 bonds, which is really an octet, so we would need to move electrons to satisfy that carbon. Okay. There was also a statement, oxygen is supposed to have 2 bonds. Okay, and it only has 1. So let's move one of those down, right? Now the oxygen has 2 bonds. So now the oxygen argument that you had should be like, oxygen's cool. But
Carbon doesn't have the octet.
the carbon doesn't have its octet. So you're like, oh, that's still bad. So what do we do to fix that? We move another pair. Where's another pair?
On the oxygen.
On the oxygen, and our resulting structure becomes a triple bond. Unfortunately not centered. I don't know if that bothers you, but it bothers me. So fix that a little bit. Okay. So is this structure now valid?
Yes.
No, it's wrong because
The formal charge.
I didn't assign formal charge. I have to assign formal charge. So I could go through and test this out. For that carbon, I'm just going to pick the carbon and the oxygen. You should be able to prove to yourself that the other ones are neutral. For the carbon, I come in with 4 valence minus the number of bonds. 4 minus non-bonding electrons minus 0. And I get what charge?
0.
0. So cool, that looks good. How about for the oxygen? 6 minus 3 or 2, depending on how you did it, based on how I wrote it or versus how I said it. And I would get what for the oxygen? A +1. So the oxygen would be a +1. Is this structure now correct?
Yes.
Are you happy with this structure? Those are 2 different statements. I'm always happy with the correct answer. No, you're not.
Is it 4 minus 0, or is it supposed to be 4 minus 4 equals 0?
4 minus 4 minus 0. One is the bonds, one is the non-bonding electrons. I guess I could say add the equals there. Everybody looks at it and they're like, yeah, that's totally cool. I have no problems with that whatsoever. What's that? And some people say it has charge. Well, shouldn't it have charge?
Yes.
Yeah. So that's okay.
Why would the carbon take
I don't understand. Elaborate. Why would the carbon take that lone pair from oxygen? What do you mean? Why do you have a problem with that?
If oxygen is more electronegative and it wants to grab the electrons more, then why would carbon take the electrons from something that's more electronegative than it?
Everybody hear that? Oxygen is the second most electronegative element on the periodic table. It is the most by far in this structure. And yet, we're saying the oxygen should be positive.
That's what resonance structures.
That sounds pretty weird. I don't know that I like that. So you're suggesting that this structure is bad and that really it should actually be written something along these lines with our hydrogens and then carbon, double bond, oxygen. The oxygen has its pairs of electrons. Okay, because the oxygens, no, I'm not giving you the electrons. Okay, but then what would happen? Carbon wouldn't have its octet. Okay, so you're challenging the octet rule number 1. Okay, that's okay. But let's just say that it's okay and sign formal charges. When we go through to assign the formal charges, we'll find the oxygen is now 0. Well, that's good. It went from positive to 0. That makes sense. And the carbon is now a positive 1. Okay, well, which of those two structures is correct? Okay, so should we try it? Double bond, hand up. Triple bond, hand up. Really? I got to choose one of them? Unfortunately, no. Only one of them is correct. Title of the slide gives us away. Best Lewis versus useful Lewis. One of those is the best structure. If you're asked to provide the Lewis structure, that is the correct answer. If you were asked to figure out something about the reactivity of this compound, the other one becomes more useful. And it all comes down to our priority for our best. Number 1 rule for best structure is satisfy the octet, which means get asked to draw the Lewis structure for this guy. It's the one with the triple bond. And that may be cringeworthy because you're putting a positive charge on that oxygen. That is the best structure. Okay? However, if I want to predict something about how this molecule forms a bond with another one of the things that I will do is look for charges. Can that oxygen accept electrons from an atom outside this structure? Why not? It has 8 electrons around it. Another atom cannot react with that oxygen. If I instead draw the best worst Lewis resonance structure, I can now see that the oxygen's not likely to react. It's going to be the carbon because it is missing an octet. A secondary atom's going to come in and react with the carbon. Okay. So when we're looking at Lewis structures, we need to be cognizant of 2 directions. What is the Lewis structure and what is something useful that I want to use and move forward? Okay. And ultimately that splits on a definition. You have to know that difference. That's the priority for best. Achieve your octets first, worry about charges later. Yes?
For the oxygen, does it matter, I guess, which side it goes on of the second carbon?
Are you talking best or useful?
Either one. Like, does it matter if the oxygen is above the carbon, the side of it, or below it? Does that matter?
Okay. I know where you're going with that. When we look at this, does that represent the shape of the molecule? Okay. Some people are hesitant, some people are absolutely no. Right. Anybody that had me before should be screaming, no. Lewis structure does not define shape. Lewis structure just says those things are connected. Where they are spatially, I don't know, but they're connected to that central structure. Lewis structure says I have 2 legs and arms connected to my body. It does not say that my two legs must be at the bottom and my two arms must be at the top. Right? What tells you the location of where those things are? VESPER, valence shell electron pair repulsion theory. And we'll get into that, but that's not the next example. How are we doing with Lewis structure? You guys okay with it? Think you got it? Do we need another example? Okay, I heard a yeah. So let's take, I'm going to leave you to hang on the CO2 and the CO because I think those are easier. Draw a Lewis structure for C3H8O. And I'll give you a minute and a half. So what's the right answer? They're all right. Are they resonance structures?
No.
No. The only thing that moves in resonance is pairs of electrons. What moved in each of these cases? The atoms changed location, so they're not resonance. Okay? These are distinctly different representations for the same formula. Okay? Which technically is not different, believe it or not. Okay? But we'll get into those definitions later. Okay? So resonance. Resonance is not changing the location of atoms, it's changing the locations of electrons. And in particular, only two types of electrons are allowed to change locations and still be resonance. Okay? Which two types? As a hint, the structure drawn here has resonance capabilities.
Well, it's more, you can switch the double bond,
I can change the location of the double bond.
which is why there's resonance, because each version is technically correct. As you said in the play positive.
Yep. So each of these, I'm not going to draw the other one. Okay. Whoa. Are resonant structures of each other. So what electrons moved to go between those two drawings?
Double bond.
Okay. We could say a double bond. Unfortunately, we don't have the proper terminology yet because it's hybridization theory that gives us the proper terminology. What we're going to say is multi-bonds can move. Well, what's not a multi-bond? A single bond. So a single line cannot move. Because if you move that single line, you've broken the atom connectivity, and you're now changing atoms. Okay? So it can only be a multi-bond that changes. Okay? We'll get into the details of what part of the multi-bond is moving as well. What's the other thing that can possibly move? Non-bonding pairs of electrons. Okay, so now we can get at the question of how do they move. Okay, well, we said the multi-bond moves, so let's take the multi-bond. Right? So that's it. Everybody acknowledge that that is the multi-bond?
Yep.
Okay. I want the multi-bond to move. So I'm going to move it here. Okay. Does everybody agree that what I just said makes sense? That the multi-bond is moving here. Okay, and that would appear to be this result, right?
Yes.
Almost. What do you mean almost?
You've got too many electrons around the oxygen.
If we look, all I've shown the motion of is the multi-bond. Did those electrons move?
No.
No. Which means in my drawing,
You gotta move.
I would need to have that. What's the problem with that?
It's too many.
There are now too many electrons around the oxygen. This structure is invalid. That means this arrow on its own is also invalid. I cannot draw that arrow by itself. But the action of drawing the wrong structure can now draw attention to the issue. Okay, that oxygen has too many electrons. So what could I do to make sure that oxygen doesn't have too many electrons? Or what else is an issue here?
Draw an arrow back up.
I drew too many up top, right? Because up top, there's not that one. Right? So really, I want one of those electrons to be up here. Okay, so that should move down, and then these electrons should move up here. Right?
Yes.
Okay. There's a big issue with this. Where are those electrons moving through? They're moving through the carbon, they're butting into the multi-bond that just moved down. Can they move through the carbon? No. So where are they moving through? Space. So every time you walk by an electrical outlet, you're like, I don't want to get near that because I don't want to get shocked, right? Because electrons would come jumping out and hit you in space. Is that true? No. Why? Because electrons can't jump through space. That arrow is invalid. If that arrow is invalid, you just screwed your entire system for getting across to the proper answer. So if that arrow is wrong, what does that mean? This arrow is also wrong. Okay? I get complaints about this. You show the wrong answers all the time. I show the wrong answers all the time because if I don't show you the wrong answer, you'd write the wrong answer on the exam and don't acknowledge that it's wrong until after the fact. Okay? We need to understand how our electrons move. We need to find the source of electrons and adjust and move from there. So how can we look at this and say which electrons I should be targeting first in my representation to move from one resonance to the other? Whoops. Because this is the structure I want to end with. I guess me jumping over the table made more sense. There is an electrical outlet back there. I wasn't just pretending.
Can your double bonds go up to they're above it?
Okay. So you're again starting with the double bond. Okay. You're saying the double bond is the most reactive thing here. Okay. There's a massive issue with both of these structures. What is that massive issue? There's no charge shown. What happens if I go through and evaluate charge? I'll notice that the oxygens are negatively charged. Which electrons should I be moving first? The multi-bond or the lone pair? Why the lone pair? I want to minimize the charge. Those are the highest energy electrons. They're charged. I don't want to touch the multi-bond first. I'm not saying you're wrong, but it's a question in the order and how you're processing and thinking about this. Where do I want those electrons to move? I want them to move to the space where the sigma bond is so that I have more electrons there, thereby making a double bond. So I will take my electrons from my source, my highest energy source, and move them someplace else. The problem with just that single arrow is that I would end up with that as an answer. Is that a valid structure? No. What's wrong with it?
There's too many.
There are too many electrons on the carbon. Okay? So that again means that this single arrow on its own is invalid. That doesn't mean the arrow itself is invalid, but on its own it's invalid. I cannot draw this new structure. But drawing the wrong thing can help me figure this out. That carbon has too many electrons, which means I have to move electrons. What electrons am I allowed to move? Multi-bonds or lone pairs. Are there any lone pairs on that carbon? Why am I only looking at the carbon? It's the one that's breaking the octet. So I want to move a multi-bond. How many multi-bonds are to that carbon? 2. Which one do I move? Okay, either. That's the answer I want. So one suggestion was I move the one that I just moved in. So I moved a pair of electrons in, and then what am I going to do? Move them back. St. Young Frank, put the candle back. Sorry. Would that result in this structure? What would our resulting structure actually look like? Are those arrows wrong? No. Are those arrows productive? No. Okay. So one option was to move the multi-bond right back to where it started. That's probably not the best option. Let's take a look at what happens if we move the other one. So I want to move those electrons now somewhere. Where should I move them? Okay. There's 2 answers. What are the 2 answers? Oxygen and carbon. We won't even worry about that one for another issue. Okay? I can either move them to the oxygen or towards the carbon. If I move them towards the carbon, what happens?
It's too many octets.
I would still exceed the octet on the carbon, which means don't move them any direction affiliated with down, which means don't even move it towards the other oxygen to the left. We need to move those electrons up. The result being my new structure. Notice in each of these cases, I'm trying to make sure my arrow shows very specifically the start and the end. My electrons started, my first arrow started at the lone pair and ended at the bond connecting them. The next arrow started at the bond and moved to the atom. Grading work by hand, I can't tell a difference, and usually it's not worth a fight with a student, because you'll be like, no, this arrow that I'm drawing is totally coming from the bond, not from the carbon. Really? Really? Right? It's not worth the fight. Guess what smart work does for me? It forces you to identify exactly where your electrons are coming from and exactly where they're going. Okay? Another reason why I like smart work. Okay? That's how we move our electrons. We find a source, okay, and we move them. Our multiple bonds are the only or one of our sources, which we'll learn better as pi bonds, and non-bonding pairs. Okay? Between those two, I want to decide which one is the highest energy. That's the one that's going to move first. Okay? If it's charged, it's by definition going to be a non-bonding pair. Okay? How do they move? We can go from bond to atom. That was our second arrow. And we can also go atom to bond. That was the first arrow we showed. Okay? Make sense? Okay? One of the things that we also have to realize is that our structure, well, that would have been nice if I had the other structure drawn here, but since you guys have awesome notes, you can look at it. The two structures that we had, okay, are pinned. That means the top oxygen is different from the right oxygen, different from the left oxygen. Okay? It's like in biology. You cut open the frog and pinned it down. When you turn the frog, you know you turned the frog. Okay? Unless you did something really gross to it. In theory, right? I don't know. I don't dissect frogs. Okay? So it's pinned. It doesn't move anywhere. So if the double bond appears to change locations, it's not because I rotated the structure, because I'm looking at resonance. Does the structure rotate? Yes. Am I responsible for knowing that it can rotate? Yes. Do I need that yet? No. It's pinned. Okay? So when we move to another example, we again find our source, move electrons within the immediate vicinity. So we'll go bond to atom, atom to bond. Oh my God, who's at the door? Verify your octet is satisfied. If there's too few electrons, repeat step 2. If there's too many electrons, what we'll do is start breaking a multi-bond or pi bond by moving electrons away from the exceeded octet. Okay, so let's take a look at the structure down below.
So the blank is supposed to be away?
Yes. Or technically away from. I want to draw a resonance for that structure. Where's my source of electrons? One of the double bonds. Cool. Okay, I'm going to pick the top right one, and I'm going to move it which direction? Leftish or rightish? Does it matter? No. The molecule is symmetric. We don't need to worry about it. Okay, so let's move rightish, because we always want to be right. I'm going to move the electrons from that bond to the atom, because that's my rule. That's how I'm allowed to move them. What's the resulting structure? Well, I didn't touch anything else, so everything else is still there. Okay? For those of you being like, do we really have to draw all these hydrogens? You've read too far ahead. That's okay. No, you don't have to, but I'm going to. Okay? What happened? I took that bonding pair of electrons and I put all of those electrons on a single atom, that atom. Please reconnect. So there's that pair of electrons now on that atom. Is this structure correct? No. Why not?
Formal charge.
I have to calculate formal charge. So I would go through and calculate formal charge for every single atom. There's a lot of atoms there. Do I really have to calculate it for all of them? Yes and no. Did you do anything to the carbon on the lower left?
No.
The very bottom? No. So if you didn't do anything to it, should its formal charge change?
No.
No, so don't worry about it. Did you do anything to the top two carbons? Yes, so we should calculate those. So let's take a look where the lone pair is. If I look at that carbon and calculate its formal charge, I will find 4 minus 3 bonds minus 2 non-bonding electrons gets me -1. My formal charge is a -1. And now I'm like, okay, now what do I do? Except that your structure is still wrong. Right? A big tip-off. When you're doing resonance, you're just moving electrons. You're not getting rid of electrons. You're not adding electrons. What was the charge of the molecule to begin with? There wasn't. Okay. What's the charge of my resulting resonance structure? Negative. Can it be negative? No. It has to have no charge. That means I forgot something. What did I forget? That top carbon. That top carbon changed its charge because I removed a bonding pair of electrons from it. It's now positive. Is this a good resonance structure? Why not? It's charged. That's bad. Right? That doesn't mean I should ignore it. That just means it's a bad resonance structure. And if I'm asked to draw resonance structures, this isn't a good one. So I will now initiate another motion. Okay? And attempt to do more resonance to see if I can get to a better system. Okay? What electrons should I move now? The negatively charged one. I now have a choice between multi-bonds and non-bonding pairs. I'll start with the non-bonding pair. I can move it towards the positive. Am I allowed to do that? Yes. What would the result be? Backwards. Okay, that's boring. Let's not do that. Okay? I'm going to move it towards the hydrogen. I'm going to move it from the atom to that bond. What is my resulting structure? Dude, Mike, you're stupid. Thanks, guys. Just trying to show something.
You're not stupid.
Jeez. Give me a second. Let me draw it. The result would be that, right? That's what my arrow shows. So you're being like, oh, that was awful. You shouldn't have done that. Why was that awful and I shouldn't have done that? How many electrons are now around the hydrogen? Too many. This structure is invalid. That means that arrow that I used is invalid on its own. Right? I would have to add another arrow to make that arrow valid. Okay, so we'll look at my bad structure and say what arrow, so the issue is that my hydrogen has exceeded the octet. What electrons am I allowed to move? Multi-bonds and non-bonding pairs. Does it have any non-bonding pairs? No, it has the multi-bond. So the multi-bond has to move where? Away from the hydrogen, right? So I'm going to add my second arrow to show that the multi-bond goes away from the hydrogen. What is the resulting structure? Oh, it's the exact same as I already drew. Does that mean these arrows are invalid? No. It just means those aren't useful to generate a new resonance structure. Does that mean I should ignore that that's bad? No, you should try this because there will be plenty of times where you will try to do something, and if you aren't testing it, you don't know that you've hit a dead end. So find the dead ends. Do not find them on the exam, please. Okay? So that didn't work out for me, so I'm going to go back to that middle structure because I drew it so nicely there. I've got that lone pair. I can't move it towards the positive charge and be productive. I can't move it towards the hydrogen. Oh crap, that means I can't move it anywhere. Oh, I could move it down. Yes. I could move it down. What's the problem with doing that?
It's still charged.
I've now exceeded the octet on that bottom carbon. That is bad. Okay. So I would have to add another curved arrow to the previous structure. The issue is that that carbon on the right has exceeded its octet. So I need to move a multi-bond away from that carbon. If I move the one I just moved in, I go backwards. So I'll move the other one. And I will move those electrons to the atom. The result being yeah? What is the difference between the two new structures that I've drawn? Are they different energetically? The charge is moved somewhere else, okay? So are they resonance of each other? Yes. Okay. Both of those are equivalent in energy. Are they both equivalent in energy to the starting drawing? No. Okay. Which would mean I'd have to keep doing this and doing this and doing this to see what happens if I propagate this all the way through my entire structure. Okay. The process of setting this up should hopefully get you in the pattern of recognizing how you could move things. And if you continue this around, you will eventually end up with, let's go up. You will end up with this structure. And this is after lots of resonance structures, right? Lots of bad crop resonance structures. Okay, I would end up there. Is that top structure better than my two red ones? Why?
It's not charged.
It's not charged. Is it the same as the first one?
Yes. It's resonant.
Okay, it's not the same structure, but it has the same energy, which means those two are resonance structures of each other. If I asked for resonance, I would expect that top structure. I do not need all of these. What? But the only way I got to that one is by doing all of these. I wonder if there was a shortcut to how we move our electrons. Oh wait, who's at the door? There's a third way to move your electrons. Bond to bond. Right, so if we clear everything away, I could have just as easily have gone bond to bond, bond to bond, bond to bond. The answer would be a slightly weird-looking cyclic hexagon. There we go. Hexagon's the word I'm looking for. Am I allowed to move bond to bond? Yes, absolutely. But you need to understand the reasoning behind when and why you move bond to bond. Okay? The electrons can only jump very short spaces. Okay? Bond to bond is really just the combination of going bond to atom and then atom to the immediate bond. Okay? To go any further than that, what do I need? Another bond. Okay? Yeah.
So why are those two completely different structures, you said? But they
Okay.
have the same.
Why do they count as resonance structures? We've moved electrons. How do you know you've moved electrons between those two?
No, yeah. I thought you said that they were like completely different though.
So be careful with the term different. I'm using it a bit loosely right now. Okay? These are not,
Like if you were to write that, like wouldn't they be the same thing?
they are the same thing as much as all resonance structures are the same thing as each other.
Okay.
Okay? They are inherently the same thing because that's what resonance means. It's another way to draw that. Said another way, what is my name? How about now? Yeah, everywhere it's still the same thing. But I'm still constantly moving. The electrons sometimes have the ability to move. Sometimes they don't. When I was doing this, did my chest move? Don't get fancy with me. Okay? No. Okay? That's because the electrons that make up my chest weren't allowed to move because they're trapped in a single bond. They aren't in a multi-bond or a lone pair. My hand is now in lone pair or multi-bonds because they can move. Depending on which state we freeze the image, we'll see a different image. But those electrons have the ability to exist in all those possible states. The identity of the molecule is still the same. Whew. This is a massive topic. Okay? I cannot stress how difficult resonance actually is. Okay? You will move all the way into second semester and be working on a question and be like, I don't know how this works. And I'll be like, did you do resonance? No. Try resonance. Oh, crap. Now I know the answer. Yeah. Okay. Resonance is super important. It requires practice. The same deal with Lewis structure. We need to be able to understand how our molecules exist, what they look like at all stages. This is why you need lots of practice with resonance and lots of practice with Lewis structures. Okay? Ultimately, what it's going to come down to is practice with resonance, and Lewis structure is probably going to come down to doing enough of them that you started to memorize the pattern. Sorry. Okay? And that for our common elements, those are our neutral states. Boron is expected to have 3 bonds, carbon 4. So anytime I see a carbon, I should expect 4 bonds around it if it is neutral. If I have an oxygen, I expect 2 bonds around it and 2 lone pairs. Okay? That becomes inherent. By doing the practice, you've muscle memory built this in. Okay? Some people say, well, that's not that hard to memorize. Well, then we run into the issue of what happens when they're charged. Okay? So that's now another layer on top of it to memorize. And some people will say, well, if it's positive, then I know it doesn't have an octet. Really? Nitrogen doesn't have an octet when it's positive? No, actually it does. Okay? So understanding Lewis structure and where and how to place those electrons will establish this set. Okay? That's why it's there. Okay? After that, what we want to do is understand not just how those things are connected. Do I have 2 arms and 2 legs? But where the hell are those 2 arms and 2 legs? Okay? Because if my 2 legs were coming out of the side of my head, you probably would have run out of the classroom. Okay? So it is really important about where these things are located. That's Vesper. Okay? And if we draw the Lewis structure for CH4, what is the apparent bond angle? It looks like it's 90, but it's not. Why is it not? This is a 3-dimensional object. That line represents electrons. That line represents electrons. What charge is on those electrons? Negative. What charge is on those electrons? What happens when those negatives get near each other? They repel. And they will push each other away until they're as far away from every other source of electrons as they can possibly be, which gets us into our Vesper with shapes. This is where you had linear, trigonal, planar, tetrahedral, and it's good that you all forgot that because we don't care. That's where we stop. Okay? We're really only concerned about octets, right? That's 4 groups. There's our tetrahedral shape. Okay? That's where those geometries come in. Okay? Again, why is that important? If my leg is coming out of the top of my head, you're going to have a problem with that. The same thing's going to happen with our molecules. They won't be able to interact the way we would expect them to because we aren't representing them correctly. Okay? Are all electrons the same? If I draw out CH4 versus NH3, do I get the same representations? Okay? And as a quick review, remember with Lewis structure, we have a box around our center atom. Are there electrons on each face of that box? Yes, which means 4 groups of electrons, which means tetrahedral. Nitrogen, NH3, excuse me. I got a box around my center atom. Do I have 4 groups of electrons? Yes, what's the shape? Tetrahedral. Would I expect those to both be tetrahedral? No. Why not? Is the lone pair different from a line? Yes, that's why we draw it as 2 dots versus a line. It's This is why we do that. Okay? We've now accented the fact that they're different. That lone pair is associated with just one atom. The line is associated with two. The line is further away from the structure. The lone pair is closer. That forces a geometry change ever so slightly out of the tetrahedral shape. It changes it to become trigonal pyramidal or pyramidal, not trigonal planar, because there's a fourth group of electrons that prevents the planarity. Okay? So we have to be aware of those. So when I say we don't need to worry about more, I'm talking about the other electron geometries, the trigonal bipyramidal and the octahedral. I don't care about those. Tetrahedral and up, but I also care about the non-bonding pair shapes. Okay? This gets me my trigonal pyramidal, largely all nitrogens, and the bent shape, which is largely all oxygens. Okay? Can I oscillate into, say, trigonal planar? Yeah. Where do I have three groups of electrons but still a carbon? You can't do that. Three groups of electrons. Carbon. A carbocation, a positively charged carbon, is trigonal planar. Is that going to change how that carbon sees the rest of the world? Hell yeah. Okay? So we need to be able to acknowledge these shapes, account with them quickly. That's where your Gen Chem textbook had a summary of it. I don't know if ours does summarize this, but here's a summary for you guys. Okay, the tutoring center also has a summary. Anything lower than tetrahedral or higher order than tetrahedral, ignore. Put a line through it. Cut it off. I don't care. Okay, we want all those. Bond angles, sort of important. I might ask a question or two about those, but not a huge issue. Okay, what I'll be asking about is how the bond angle changes. Why, when I move to trigonal pyramidal, does the bond angle between the atoms get smaller? Here's a tetrahedron, right? There's the three bonds, or three atoms. There's the center atom, and then the fourth atom is my wrist. If that fourth atom is a pair of electrons, where does that pair of electrons then go? It goes closer to the center atom. What does that mean these guys do? They're going to move away from that closer source of electrons, which means the bond angle decreases. That's where our shapes are coming from, or why we get those subtle bond angle changes. Okay? God, this is such a long slide. So we're going to move to this. If we were asked to draw the structure of the compound hinted at C5H12, I'm going to do this kind of fast so you guys can attempt to do it at the same time. What I was fishing for was you guys to come up with something along the, for a Lewis structure.
It's 12:44.
I know, that's why I'm talking really fast. 1, 2, 3, 4, 5. Yeah, all those are hydrogens. That was what I was hinting at. But again, just like we learned already, I was going to be a jerk and say this was actually the answer I wanted.
But it's not.
Okay? How would you know? You wouldn't based on that formula. What information would you need? A structural formula, sometimes also known as a condensed formula, okay, that better represents the atom connectivities between those. If I went through and drew the Lewis structure, I already did. Okay? That's really tedious and time consuming. We want a faster way. Okay? I could go through and show Vesper and show the proper bond angles. Okay? This is where you end up seeing kind of a zigzag shape come out, 4, 5. And then I could still show in all those pieces. That's a CH2, CH3, CH. Okay? That's still tedious. Okay? I could also add more detail into that and draw attention to the hydrogens, okay, and their exact representations relative to the rest of the structure. Right? Hydrogen, ooh, a wedge, meaning hydrogen is towards you with a wedge. Dash means the hydrogen's going away. Okay? That becomes really insanely tedious. So what do? We imply all of the hydrogens to satisfy octets. We imply carbons as points. and I can now get my final answer. I know that that's a CH3 at the end because there's only one bond shown. Because I know carbon has 4 bonds. If one is shown, the other 3 must be hydrogens. The hydrogens become implied, which is really where I wanted to end. We'll start with this that next day. But this is looking at our abbreviated drawings. This is ultimately what you need out of Lewis structure.